from wherever you are in the world. Again, welcome back to the second day of this particular workshop. And as we had discussed last time, I am going to talk about two key ideas today. One is this key concept of hypothesis testing regarding geosciences, and then I'll show you some code on how to do basic linear regression. Again, in the actual course, we'll go into the details of the mathematics and what it means, because linear regression is just a part of what is called least square regression. And we are going to go into the details of how we calculate this R square value, what is the mathematics behind it, how do we get those numbers, and so on and so forth. Again, obviously, there would be many more topics, but with reference to what I'm covering today, I wanted to share some of those details. And again, after the hypothesis testing and an example and the linear regression aspect, I'll open the floor for any technical questions. If you want timings, fees, and all that stuff, please refer to Mr. Nikhil. He is aware of all of that. I am able to answer technical questions only, so related to statistics, geology, Python programming, so on and so forth. All right. So without any further ado, let us jump into this concept of a hypothesis. Now, we are all aware that geology is an applied science, and in science you have to have a hypothesis, and that hypothesis is essentially created based off of an observation and a question that has been raised due to the observations. And so what I want to do is quickly talk about that. So typically, when we do any kind of statistics, we have gotten to a point where we are asking a very specific question. And to answer that question, we have to, in statistics, set up what is called a hypothesis. And there are two kinds of hypothesis we typically develop. One is called the null hypothesis, and the other one is called the alternate hypothesis. Now, what is this? So, for example, you make an observation that if you continue to heat a block of rock, its temperature rises. Okay. So after that observation, you might ask the question, so adding energy to the body increases temperature. Now the answer seems to be obvious. Excuse me. But then again, in science, you have to evaluate all possibilities before making a definitive conclusion. And that's what hypothesis testing is all about. Now, then you would generate all kinds of different tests to see if what you are proposing is indeed the case, or is there any exception, or there are many exceptions, or what you have proposed is absolutely incorrect. Science really doesn't care about what our feelings and our desires and things like that. It just is, in a way, very neutral. So in application of statistics in geology, we also set up some problems. So I'll give you a problem to start off with. In fact, we will start with the geological problem. So let's say, for example, you are a paleontologist and you have gone out in the field and you have collected a bunch of fossils, all right, a specific kind of fossils. And somehow in the literature, it has been proposed that a lot of paleontologists have worked on these kinds of material, and they have generated what is called the population mean of the length of this fossil. So this fossil, you can measure the length and width of the fossil, And it turns out that thousands and thousands and millions of these have been measured by many scientists, and all of the data has been collated. And it turns out that the population mean has a certain value, let's say, 15 millimeter or whatever. And the standard deviation is 5 millimeter. Okay. Now, what do these terms mean? We will talk about those. Okay. So we will talk about these in detail when it comes to the actual course, because we will be walking through what is population mean, what is sample mean, and so on and so forth. All right. So let's assume you have somehow figured out population mean of length for a particular fossil. Now, you as a paleontologist have gone out in the field and you have collected some similar fossils, and you have also you have collected not one but multiple of them, and you have taken them back into your lab and you have kind of measured their lengths. And your initial hypothesis is that these two, you want to test, are they the same fossil or are they different fossils? So then to answer the question, we are going to do a test that is called the Z test. Don't worry about what that is. We will talk about that later. A Z test is essentially, long story short, is when you compare your sample mean with a global population mean and try to figure out how similar or how different those means are. If the means are different enough, then it is very likely that the sample that you have collected doesn't come from the population of the same fossils. It could be another type of fossil. Again, I'm not a paleontologist, so excuse me if I am not using the exact terminology. So then what we do is we set up two hypotheses. One is called the null hypothesis, and this hypothesis is typically the hypothesis of no difference. So you are going to say our null hypothesis would be that the sample mean that you have collected is the same as the universal or population mean for that particular fossil. Okay. Now, since you have developed a null hypothesis, you have to be aware that the alternative is also possible, and that is the hypothesis of difference, that there is a difference and the difference is significant, and that is called the alternate or alternative hypothesis. And in this particular case, the hypothesis says that the sample mean that you have collected differs or is not the same as the population mean. Note, we are not talking about is it greater, is it equal, is it less than. Okay, we are saying that they are not equal. All right. Now, based on whether you are saying it's not equal, or if you say that the sample mean is greater than or less than, there are two subdivisions for the alternate hypothesis. One is called the one-tail test, and the other one is called a two-tail test. When you say that the alternative hypothesis is not the same, then you have to do what is called a two-tail test. Why? Because you are not providing a direction whether it is smaller or whether it is greater than the population. However, if you specify that the sample mean is greater than the population mean, then you are proposing a very specific direction. And for that, we do what is called a one-tail test, because you have already provided the scenario. Now, then the question arises is, well, why do we want to do this one-tail test, two-tail test, and null hypothesis? How do we test this? Well, it goes back to all of this probability business that we briefly touched upon. Maybe we talked a little bit about randomness, and then how I said that as we deviate from that randomness, we get an order. Now, what are the chances of a particular observation to be either ordered or disordered is what probability is all about. So then we essentially have to figure out how confident I am regarding discussing that the observation is ordered versus disordered. So let me put it in simple terms. Let's say I make the proposition that there is a 70% chance of rainfall right now. Okay. So that means I am assigning a certain weight or a certain confidence with the outcome. Okay. Now that outcome has to be backed up by certain mathematics. Let's ignore that for the time being. Okay. And that is what the one-tail test or two-tail test is going to help us deduce. Now, again, out of context, this kind of sounds really weird, but what if I am wrong? I'm a human being, so I can make mistakes in my mathematics or in my collection of data or in my interpretation of the numbers. And so a lot of things can happen. So similarly, there is something called the I'm trying to get this PowerPoint to move, but okay. All right. So I can make mistakes. And there are two types of mistakes, or these are called two types of error. Okay. And the easiest way to explain this is through the tables that I have over here. So let's look at just the first top table. The top table has three columns: truth over decision, hypothesis is either correct or hypothesis is either incorrect. Now, let's say that you have said that the population mean and the sample mean are the same. And let's say that is the truth. Okay. And for whatever test you have done, you have accepted that hypothesis. Okay. Now, if you have accepted that hypothesis and the hypothesis is actually correct, then you have taken the correct decision. All right. But what if your hypothesis is incorrect? Now, you might ask the question, what do you mean by hypothesis is correct or incorrect? Okay. That simply boils down to the question that you have asked. Is that meaningful or is that not meaningful? And whatever test you have applied to check that hypothesis, is that correct or not? Okay. But so whatever null hypothesis you have proposed, you have accepted that null hypothesis, but in reality, that null hypothesis is incorrect. Then you do a type 2 error. Now, what does that mean? That means you have accepted a false idea. Okay. So that is called a type 2 error. Now, let's go back to another scenario where you have rejected a particular null hypothesis, but the hypothesis is actually correct. Okay. That's called a type 1 error. Okay. However, if you have rejected the hypothesis and the hypothesis is indeed incorrect, you have taken the correct decision. Okay. Now, we don't have time for a detailed discussion of this, but that is why I've put in an example right over here, where I have said that the truth is either the sample is from the population or the sample is not from the population. Okay. But somehow there are two decisions. Either you have made the decision sample mean and population mean are the same, or sample mean and they're not the same. So let's say you have decided that the sample mean is equal to the population mean. Okay. And in the case of sample is indeed from the same population, you have made the correct decision. But if it is not, okay, so for example, the statistical tests, the sensitivity of the statistical tests you have chosen did not catch something, then you have committed what is called a type 2 error. Okay. And to cut a long story short, type 2 errors are bad things in statistical tests. You do not want to commit a type 2 error. Okay. Now, what if you say that the sample is not from the population, but the sample actually is from that population? You have committed what is called a type 1 error. Okay. Otherwise, if the sample is not from the population and you have said this is your decision, then you have taken the correct decision. Now, this geology thing could be a little hard to wrap your head around. Let me put it as a justice system problem. Let us say you are a judge, okay, and you have a person in front of you who is being judged, and let's say that man or person is actually guilty. You know, that's the truth. The truth is he or she is guilty, but you don't know that. Both the lawyers tell you this, that, and the other, and after looking at all the decisions, you say that the person is not guilty. Okay. So what you have done is you have committed a type 1 error. That means the guilty went free. Okay. Again, consider the scenario. The person is actually not guilty. That person did not commit any crime. Okay. But based on whatever tests, legal tests that you had, you pronounce that man or woman or that person as guilty. And you send that person to the gallows. Okay. And so what you have done is you have sent an innocent person for punishment. Okay. That is called a type 2 error. Okay. Because so understand this, if you sign the death sentence of that person, an innocent person is getting killed where he or she is not guilty. Okay. So that's the way of understanding error types. So what can we do? So our goal in statistical test would be to reduce the chance of a type 2 error. Okay. And so in statistics, when we give a percentage, what we do is we create what is called a level of significance or an alpha value. Okay. And what is that? In statistics, the probability of committing a type 1 error is called the level of significance. Okay. And the alpha value must be set for any running statistical test. Okay. It doesn't matter what you do. It doesn't matter if you do a geostatistical test or a simple comparison test or a linear regression and analysis of variance. It doesn't matter. If you do a statistical test, you have to set a hypothesis. You have to set an alpha value or a significance value. Okay. And typically, for any statistical test, the goal is to remove or reduce the probability of committing a type 2 error, where the false null hypothesis is accepted. Okay. And most of the time, you will see that we say we either set the alpha value at 95% or 99%, or in the worst case scenario, 90%. Okay. That means you are leaving a 1% or a 5% chance of a type 2 error. Okay. And that is very critical in developing a hypothesis and choosing a statistical test. Okay. Now, the first thing, any statistical analysis that comes across your table, the first thing you should look for is what is the level of significance for whatever test that has been performed. All right. So what I'm going to try to show you is well, it's very difficult to show the performance of a particular test given something, but I'll show you how we set things up. So allow me to share a document that I am developing. So give me 2 seconds to open up the document. And where is the document? Yes. Okay. So in this particular problem, hopefully you can see my document. What I'm going to do is I'm going to perform a Z test. Again, I told you what a Z test is, and specifically, this is a one sample Z test. It's just a fancy way of saying I am going to compare the mean of a sample of brachiopod fossils with the population mean for that brachiopod fossil. Okay. And in this particular problem, I have set the population mean to be 14.2 and a standard deviation of 4.7. And we determined that the variance is 22.1. Now, our hypothesis is that the sample comes from the population. So that is our null hypothesis. And our alternative hypothesis is that mu1, which is the sample mean, is not the same as the population mean. Okay. Now, since I have not indicated a direction, this would be a two-tailed test. Okay. Then we set the level of significance. Okay. The level of significance is 0.05. Okay. That means I am going to allow a 5% chance of a type 2 error. Now that's good enough. I mean, typically, if we have large enough data set, we don't have to worry about this. Okay. And the formula for the statistic is given. We calculate certain values, and what we wish to plot are the values on a normal distribution curve. Again, it's not possible for me to show you everything in this very short period of time. So you have to sort of trust me on this. And there is a region we call the area of rejection or critical area, which is towards the far end of the normal distribution. Now, if your test value falls in that, you say that at 95% confidence, I can reject the null hypothesis. Okay. Now, statistically and physically, that has a meaning. Okay. And that means if I made 100 such measurements, 95% of the times, my value is going to be significantly different than what I am comparing it to. Okay. So that is the meaning of that. For the two-tailed test, the area gets divided into 2.5%, again at two ends of the curve. All right. We can, I could plug in the numbers here. The Z value is calculated. And then so this is the test statistic. This is the value we have found. And then when we look up the Z-score table, using the Z-score table, we find out that the critical area, the value is way larger than what it should be from the normal distribution curve table. Okay, and so we reject the null hypothesis in this particular case. Okay, therefore, we can then say that the sample I have collected and tested is not from the population that you had originally thought it was from. So they are possibly not the same fossils. Okay, so that is how we can actually quantitatively make a statistical distinction between samples. All right. Now, I won't add any more to that. Again, we would be doing these a lot more slowly, a lot more carefully to understand these in this actual statistics class, the course. But for now, you have to kind of understand the kind of material we would do. Now, in the actual course, we would actually do problems by hand first, and then we would write a generic Python code that would do that. So I believe I've written a Python code for that. So yes, right there. It's a different problem, but we could write a Python code. I'm not going to repeat this. This is just to show you that the kind of things we will cover. And so you can calculate the Z-score and actually write a conclusion. So see, I have set it up so that at the end, instead of just throwing out numbers, you are actually going to get a conclusion out of it. And you are going to get an answer, either reject the null hypothesis or you have failed to reject the null hypothesis. All right. So that's the kind of things we will do. All right. So now, allow me to go back to the programming aspect. So I will launch my programming tool. So give me a second to launch my programming tool that I had opened up yesterday. And it takes a few seconds to do this. And first of all, I am going to plot certain distributions of two of the elements, and one of them is cerium, and one of them is lanthanum, and we will try to draw a linear regression line through that. Well, hopefully my program starts. Let's see here. All right. So let me share my screen again. Okay. So this is our last program that we had originally written for the other day. So now I am going to save this file as a linear regression. Same place, I'll say linreg. And we are going to write the code. Now, I'm going to, in the interest of time, what I'm going to do is I'm going to steal a couple of things from yesterday, like this particular line. So again, I am going to import a few libraries. Oops, sorry. Okay. So these are the things. So if I say my data, so I have put in my data there, so that's my data. And now I want to generate a couple of plots. Actually, I'll do two, so you can see what I'm doing. So I'll do one where the correlation is not that great, and in the other case, the correlation is actually pretty nice. So you can see the variation that is there. Now, I would write things that appear to make no sense, but don't worry, we will walk you through all of that, okay, in the actual course. Again, otherwise, you would feel that I have no clue what is going on. How am I going to understand what is happening in the real course? Essentially, in this particular line, I'm about to generate the plots, calculate the linear regression. I have generated a figure, and there are going to be two figures, and that is all I have set up here. Okay. And then I am going to actually generate a scatter plot. And then I'd say df dot LA, comma, df dot Syrian marker equals, and some of the stuff will be pretty obvious to you. So in the x-axis, I'm going to plot the lanthanum concentration, and on the y-axis, cerium. The marker is going to be a circle. Then the edge color is going to be black, and the color inside, I am going to make that, I don't know, blue. And then I am going to say that don't want to give a label on this one anymore, and this saves some time for me. All right. And now I am going to do something really weird. So please pay attention in this one. I am actually going to calculate the parameters of a linear regression. And you recall from linear regression, the equation of a straight line is y equals mx plus c. Okay. You know the values of y and x. We are going to have to calculate the slope and the intercept and the correlation coefficient and some p-value and things like that. So we are going to calculate all of that. So P1, P0, comma, val, comma, p-value, comma, standard error. Okay. And this is equal to ST. This is where I'm using the statistic library. And then I say lin regress df dot la, comma df dot ce, oops, sorry, comma that's that. And now to plot this, we need the X values generated. Some, I'm just generating some values of length now. So what I'm doing is np dot linspace, which is equally spaced values of df dot la dot mean, which is the minimum value of the lanthanum, then df dot la dot max. And then I close that bracket. Okay. And then what I am going to do is I'm going to say that the way y is to be calculated, y is equal to b0 plus b1 times x. So it's going to fit it into this particular formula. All right. Now comes the really weird part, and you will have to bear with me on this one. So the x1 dot plot. So it's going to plot this stuff, which is x comma y, pretty straightforward. Then I say line width equals 1. Color, oops, sorry. Color equals, I want to make it red. And lines, oh, sorry, line style equals that. And then I am going to say that this is the part that's going to be pretty long. Label equals R, and then within parenthesis, inverted commas, I am going to say fit parameters then I will say comma, I'll say B0 equals, or I want to say B0 is plus str of B0, oops, sorry, B0 plus then I would say P1 plus str P1. What else? Yes. Plus I would say R square. Okay. is going to be plus the str of row value square. Value square. What was that? Row value. So that would be row value squared. All right. Just to make sure that I will close this. Close that. Wonderful. Okay. So this is done. And now I will put some labels just to make our life a little easier. Dot set underscore text label. That would be LA ppm x1 dot set underscore y label Syrian ppm. Okay, and then I can say AX1 dot legend. I will say location equals upper left. All right. Now that's one done. Now the beauty of all of this is I get to do copy paste and change a few things. Control C, Control V. I get to change this to that. I will put this to that. This is this. Scandium versus uranium. Uranium, same stuff. Everything remains the same, except this becomes scandium. This becomes uranium. This becomes SC, SC, blah, blah, blah. Pretty much that's what it is. And now all I have to do is do plt dot show. And now if I run this code, it will take a few seconds, but eventually it will give me a solution, and I will share the solution with you. Now, the advantage of this writing these kinds of codes is that if you go through similar kind of data sets, it's very easy for you to just make the script run, and that's that. So it's you have to spend some time only once. The data is already shown. I am going to, wow. Wait, hang on, there is a, well, I'll show you what the mistake is, so you can actually see what's going on. So the way I have done this, I've made a mistake so that both of them have kind of gotten up together. But in essence, if I increase the size of this window, you can see the R² value has shown up. Okay. So this is lanthanum versus cerium. It's very highly correlated because the R² value is 0.93, whereas the other one is not very well correlated. I have to see my code in a second, so give me a second to look at the code. I will switch it back to the debugging part so you can see what I do. So Aha. Very simple mistake. I made it plot on the same thing. So just fix them. To save, run, and it's almost done. All right, now I can share the pretty looking plot. Okay, so there you are. You can, so if I open it up for the entire window, you can see the parameters have been plotted, and you have done a linear regression. And the parameters are also given to you, which is the intercept, which is the slope, and so on and so forth. So obviously, the B0 is your intercept, B1 is the slope, and then the R square is your correlation coefficient, which is what you are interested in anyways. All right. So the advantage of this kind of coding is you can generate multiple such. It doesn't matter if you want to correlate all of them together. In the actual course, I'll teach you how to do a correlation coefficient heat map. So instead of plotting a pair of data and then drawing this line, what we will do is generate a heat map where any pair can be compared, and there is going to be a color index that tells you the correlation between them. So to give you an idea, let me show you. I'm going to show this to you on the web. I guess we could spend 15 seconds to do that. I'm going to go to the code, close that, and wait for my browser to open up. So I can show you what a heat matrix, what a correlation heat matrix looks like. So my Windows has, my internet browser has opened up. Let me show you. Okay. Now, these correlation heat matrices are much more powerful, and writing the code for that is pretty simple. Actually, the amount of code that I wrote for what I showed you to generate that, I can do that in lesser amount of code. But again, that is all for the actual course itself, where we go through everything.